Ken Griggs, and we're talking about PhOENIX, which is the physics of entanglement, networks, and information exchanges. And as Scotty would have said from the first Star Trek movie of the new Star Trek order, this is exciting! Okay, so, and what's exciting is not just the full breadth of this theory, but what I'm about to introduce to you. What I'm about to introduce to you is something that I know a few of you have actually gone, wait a minute, well what about this? How come this structure does not exist? He talked about that this is what you had to do and blah, blah, blah. Okay, so just take a deep breath and let me tell you what it is. So when we talked about all of the possible ways that you could put loops and arrows and edges onto a vertex, I purposefully didn't tell you about one of those things, okay? So I'm just going to draw out for you a little bit, putting the loops and the arrows and all of them stuffies on our vertices. I'm just going to draw some out for you and remind you what we did. Okay, so for a full graph of with a single vertex, these are the four possibilities, okay? These graphs do not have to connect to anything else. They can exist on their own as single particles. In point of fact, we said this is the positron, this is the W minus, this is W plus, and this is the electron. Great. Now, let's see what happens when we have to actually connect the vertex to another vertex through a single edge. So we get one structure, okay? And we get another, so we get one structure, by the way, with two loops, and we get another structure with two arrows, right? Two loop structure, two arrow structure. And remember that the reigning theme here is that on every vertex, there are three of something. Three arrows, like here, right there, three loops, two loops and an edge, two arrows and an edge, but there's something missing. But we'll get back to it. Let's go down to the situation where we've got one loop and one arrow on a vertex, right? So the one loop and the one arrow on a vertex, right? So you can have those structures. The one loop, and then these two edges connect to some other vertices, and then the one arrow, and then these two edges connect to some other vertex. And then the final one that we've shown is that you've got that vertex which just connects to three different things, or one different thing, or whatever, but it doesn't have any loops or arrows. So we've got something missing here. And I know one of you creative spirits out there recognized that it was missing when you were trying to do this on your own in your own piece of paper, or even when I was talking about it. This is not a factor of brightness, so don't think of yourself as, oh my God, I'm so bright. No, just think of yourself as being creative. Okay, well, you can be bright and creative, and creativity is bright, and blah, 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 blah. But this has nothing to do with any, extraordinary feat of thinking. It's just, it's an obvious thing that I left out purposefully. And what that is you have a vertex that has a loop and an arrow and an edge. So it looks like that. Now, that specialized juggernaut is what I call Q. Yes, I said it. So we could either call that a Q-Quark or just a Q particle, okay, or a Q chunk. And I named it Q for many reasons, certainly because when it came into being, we were in the days of Star Trek: The Next Generation. And I was fascinated by the omnipotent character of Q, played by John Delancey. So kudos to you, Mr. Delancey, for your brilliant role of Q, and for the writers and the directors and all of the other people who played in Star Trek to make that possible. Thank you. Q has special properties here. First of all, Q has an arrow and a loop. Now that arrow and loop together, when we try to put it into a slot on a matrix, we have to add them together. We have a +1 from the loop and a -1 from the arrow, and added together is 0. Okay, so in so many ways, that quark, or that chunk with a Q at the end, that chunk actually acts like a neutral entity. It has no charge associated with it. That's one of the critical anomalies of this beautiful queer character. And I use queer, of course, because I happen to be gay, which if you didn't know, because you don't know me, I am now informing you. You were talking to a gay black physicist. Okay, whatever. So if you happen to be conservative, you might want to just shut it off right now and move on. But for everybody else who understands that being queer is absolutely beautiful and okay, thank you. But I'm not really asking for that from you. I just want you to understand what's going on here and to know that that's another reason why I named this the Q-Quark, because it is queer. It is curious. It is great. And that doesn't start with a Q, I know. Okay, so we have our queer quark, or our Q-Quark. And that queer quark can combine with all of the other structures that can combine in our theory. That's its role. Just like all of these other structures, the U and the anti-U and the D and the anti-D and the chunk of a photon and all of that stuff, they're all meant to be the subspecies, the things that you can combine in order to make these larger graph structures. And these larger graph structures are, in point of fact, the particles, the things that we should be able to observe in nature if they'll allow us to observe. So I did want to point that out because it is a curiously beautiful thing. And let's just get to one curious nature of this Q-Quark, and that happens to be that this, when you make one of the first particles with it, okay, it's a V equals 2, V meaning the number of vertices, V equals 2 particle, so we start with 2 vertices, and each one of those vertices has that structure. So there's a loop and an arrow on each vertex, and then there's an edge connecting them. So it looks something like that. This is a new thing. Curious, right? We now have to identify, what the hell is this thing? So, what is it? Well, what we know, or what I'm going to share with you, is something beautiful. Let's write out the matrix for this curious structure. So after I label each vertex, and I create a 2 by 2 matrix and label each of the columns and the rows. Okay, well, let me just draw out the slots. When I do that, and I fill in the slots, so I'm going to fill in the slot here, right? So for vertex number 1, it's a +1 because of the loop, and it's a -1 because of the arrow, and you add them together, and it's 0. So the first slot has 0. Bloop. The second slot down here, right there, has 0. Well, that's curious because there actually is something on those vertices, but those things act as if there's nothing there. And what that kind of means, just to let you know, is that if you tried in the laboratory, if there was a particle that had these quarks hanging off of them, and you in the laboratory tried to see it, how would you do that? Well, you would shoot something with a charge at it. So, for example, you take a high-energy electron and shoot it at the structure. Because what you want to do is you'd like for there to be an electrical scattering. You'd like for the electron to somehow scatter off of this vertex and show you, by its scatter pattern, what that vertex is. Well, when that vertex has nothing on it, or it, like the chunk of a photon's chunk has nothing on it, which means that if you shot a high-energy electron at a photon, it's not going to scatter off of the vertex of the photon. You will not see a scattering. Same thing is happening here. This has something on it, but as you shoot that electron, the electron is going to get a 0 net effect. So it's not going to scatter off of this queer vertex. So I just wanted to point that out. It's not something that you can readily see in the laboratory. So you're not going to easily find it when you're conducting your QCD experiments. That's a beautiful thing. And that's what makes Q so queer. Okay, but we're going to go on and then define what that edge is between them. That's a 1, so that goes into these slots here, the 1 and then the 1. Okay, so the matrix for this particular queer V = 2 particle looks like that. Now, we have to ask the question, what does this transform into? Because that's what we're always curious about. Is there something that can create this queer particle? And the answer is yes, absolutely there is, or else I wouldn't be introducing. Actually, that's not true either. I'd be introducing it to you anyway. But yes, something can create this. And the something that can create this, I'm not sure if you know this matrix well enough, but this matrix is a special matrix in matrix theory. And we know that the eigenvalues of this matrix are 1 and -1. So if we go through the process that we went through before, finding the characteristic equation and whatever, we can pony out what the eigenvalues are for the matrix. And when we do that, we find that the eigenvalues are 1 and -1. Now, the eigenvalue of any ordinary or any diagonal matrix is just what's on the diagonal alone. So if I know that the eigenvalue of this matrix is 1 and -1, in fact, let's just quickly do it. Okay, so we're looking for the characteristic equation. And the eigenvalues is when we set that equation to 0 and solve for our monomial term, our one variable. And when we solve for it, the solutions are what we call the eigenvalues. So let's find the characteristic equation of this. And as you recall, it's the we're going to call this chi1. It's the determinant of chi1 minus lambda 1, right? Remember that? So to find the eigenvalues, we set this equation equal to 0. That's how you find the eigenvalues. In other words, you'll be solving for this variable. So we're going to write it out, do it out. So we have 0, 1, 1, 0 minus lambda 0, 0, lambda gives us minus lambda 1, 1, and minus lambda. Okay, so the matrix that's a consequence of all of this stuff is this matrix here. Now we take its determinant. And the determinant, by the way, just for people who are somewhat new to this, the determinant is what makes the matrix into a scalar. Scalar meaning it's not a matrix. It's just a simple number, or polynomial, or monomial, which is really a single number when you get the solutions. Okay, so in this case, it becomes lambda squared minus 1 equals, in this case, 0. So this is our characteristic equation that's going to give us eigenvalues, okay? And the eigenvalues are the solutions. What are lambda that actually satisfy this equation? And when we solve this equation, what we get is lambda minus 1 times lambda plus 1 equals 0. Okay? That's what we get. And when we solve for lambda, we know that lambda can be equal to plus 1 or minus 1. Those are our solutions. Now, at the bottom. Now, what that means is that and this is part of the properties of doing eigenvalues and the rest of the stuff, but when you find the eigenvalues of a matrix, it really just becomes a new diagonal matrix where those eigenvalues are all along the diagonal. That's why mathematicians and people who deal with matrices go through with this, because when you have a diagonal matrix, a lot of your multiplication becomes so much easier. So in our case, our diagonal matrix will look like a 1, 0, 0, minus 1. This is what it means to be a diagonal matrix, okay? Now this structure actually has form in PhOENIX. So the graph that's associated with that structure is, in point of fact, the W plus the W minus. Boop, boop. So that's W plus and W minus, right? Those are the two graphs that give rise to this matrix. Brilliant! Not brilliant for me, but brilliant just because it works so beautifully. Okay, I didn't plan on this working like this. I had hoped it would, but now we see it actually does. So what we found here is that this structure, the structure that we diagonalized to get this eigenvalue structure, so we started with this Q-Quark structure, and now we've identified that that Q-Quark structure actually can decay into a W plus and a W minus. Right? That's what we were able to show. That structure there was the matrix 0, 1, 1, 0. And the new structure is the matrix 1, 0, 0, minus 1. That's what I'm trying to say. See? So that was that. And we showed that these two, that this can be transformed into this just by diagonalization. Which means that there's a transformation matrix that does that. Okay? And in fact, it's the same transformation matrix we've been using all along, the same Hamiltonian. We don't need to get into the details of that. But suffice it to say, go through the other lectures and you'll see how to work that out. And you can go, oh yeah, it works. Okay, it works. Okay, so what we have here is, we know from particle theory that when the W and the W minus come together, and they don't form a photon, okay, what they form is a Z particle, a Z naught. So we've been able to identify the Z naught particle. Whoa! That should be the reaction, right? Whoa! Holy freaking shit! Okay, but nevertheless, we get the Z naught particle out of this structure. So we can readily identify this as a Z naught. But I'm going to let you in on another little strange behavioral characteristic here. This Z naught can be drawn in two different ways. Okay, so that's one way of drawing it, which is where we have the loop and the arrow on one vertex, and the loop and the arrow on the other vertex connected by an edge. But the equally other way of drawing it is by introducing another strange phenomenon. We won't go too much into this, but I do want to make you aware of it. It's a phenomenon called a negative edge. Okay? That structure right in the middle. So basically what we're saying is that this particle here can be represented equally by this particle here in the matrix way of looking at it. And let me show you why. First of all, what a negative edge does is very similar to, exactly the same actually, as what a tadpole does. So a tadpole can be a plus tadpole or a minus tadpole. A plus tadpole is a loop, a minus tadpole is an arrow, and so when you have to determine what's the quantity sitting at a single vertex, you add all the tadpoles together. Well, when you have to determine how many edges, the count of the edges on the off-diagonal part of the matrix, you have to add all of the edges together, right? So if there are 3 edges between 2 vertices, as in a regular photon, 1, 2, 3, then on the off-diagonal is the number 3. Well, here, since an edge can be negative now, we have the curious case where you have 2 edges, the top and the bottom, and an edge in the middle, a minus. So plus 1, minus 1, plus 1. You add that all together, you get 1. So that's how we can readily identify this with the very same matrix that was identified with this curious Q particle. Right? They're they're identically the same matrix. But we now have these 2 different ways, these 2 different looks for that structure here. So the Q-Quark actually looks curiously photonic. Curiously photonic. But remember when we were talking about mass way back maybe in the 3rd or the 2nd inaugural sequence, whatever you want to call these lectures. But remember when we were talking about mass and we said that rest mass, is really a diffusion process. Basically what we're saying is that you look at a vertex and you ask how much information flows out of the vertex and how much information sits on the vertex. Well, in this vertex, you have a loop and an arrow. That loop and an arrow means that information is still sitting on that vertex. 2/3 of the information sits on that vertex 2/3 of the time. 1/3 of the information flows from the vertex somewhere else. It leaks away. Whether it's leaking towards or leaking away, it's leaving. It's not actively sitting on the vertex like these two things are. So in this particular situation, this vertex almost sits around. It has a sitting around quantity that looks like the U-quark, or it looks like the D-quark, or it looks like one of those other. In fact, it looks like the U-quark in terms of how much it sits around. So we would say that this quantity has rest mass. This particle has rest mass. And this particle, by extension, must also have rest mass. And what's inducing the rest mass here is this curious negative edge that seems to kind of fuck up the whole sequence of the normal affairs that we had. So here, the queer is queer in so many wonderful, beautiful ways, as queer always is, by the way. And in this particular case, it's queer because it looks like a photon, but it's got mass. This thing has mass. Okay, so we'll get back to that, but I did want to introduce that this is Z0. Z0, okay? This is the Z0 particle, the other neutral version of the W minus and W plus that can in fact be gotten to by throwing W plus and W minus together and letting them supposedly annihilate and blah, 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 blah. Okay, so we just introduced the queer terms, the Q-Quark and the queer quark and the curious quark and all of those wonderful Q terms and the best quark out there. Okay, so I just wanted to give you a grappling of that wonderful entity that I didn't purposefully talk about when I first introduced the entities. I'm going to bring this back up, okay? But it's there, and you can't ignore it. It exists, and its existence is tied to these other particles here. I'm just going to sort of map them out, okay? These are queer particles. They are the strange particles of our situation, but this one being the strangest. Now what you also see in this beautiful thing here is that you see this right here. This represents all of the, how should we call them, the regular particles. And this represents all of their antiparticles sitting on a vertex. And this represents pure energy. Remember, that was Spock. Okay, pure energy. So, antiparticles, regular particles. Kind of cool, isn't it? So what we've been able to demonstrate here is that we can now also account for the Z0 particle as well as the W plus and the W minus as we've identified them, and account for the photonic matter, and account for particle, antiparticle, and account for baryons and mesons and leptons and other entities. Now, when we started putting these vertices together, we didn't have any rules that said that you couldn't attach this kind of a vertex to that kind of a vertex. That is a huge weight off of the shoulders of particle physics, okay? That is a huge weight lifted. Let me tell you why. Because when we had those quark rules in QCD, where a quark can only be combined with an antiquark to form a meson, and then you could have 3 quarks combined to form a baryon, but you couldn't really curiously have 2 quarks and an antiquark combined to form some sort of meso-baryonic matter, and so we're still exploring that in the laboratory. What we were saying is that those other instances where you're taking what look like 2 U-quarks, combining them, give you leptonic matter. It gives you a neutrino, an electron neutrino. Or when you're combining, I didn't show you this one, but when you're combining something that looks like a U-quark with a chunk of energy, and with something that looks like a D-quark. Okay? This structure. that structure is completely leptonic. And it's in fact that age-old muon. Yes, that's a muon. Isn't that cool? Okay, so we're actually able to now find out what leptonic matter is because it combines similarly typed particles. Okay, so the similarly typed particles are the matter particles. And the similarly typed particles are the antimatter particles. And they meet right here in this energy alone particle. But this similarly typed stuff, when you combine these together, in particular these together, you get leptonic matter. When you combine these together, you get leptonic matter. However, when you cross-combine them, you get hadronic matter. Baryons, mesons, nuclear matter, like that. That's where this comes from. So this has all of the beautiful characteristics of the electron. In fact, it can, under certain circumstances, quantities like this can decay into leptonic or electronic matter. And you find that when you build larger and larger structures and this, that, and the other, you find that there's a resonance effect where the structures, and building larger structures meaning that you're adding more of these into it, okay? And as you add more of these bits of energy, you make the structure more energetic, you make it bigger, you make it more, you know, a bigger system. And so we can readily identify this structure with the muon, but we can also go back and look at muon decays and look at all of those other things to also better demonstrate that these are the structures that can and do fall out of muonic matter, and that matter at its core also has electron features to it. So it is a leptonic system. Now, one of the things that we can also do, and this stuff, by the way, I've done, this was years back. This is old, okay? This is about 10 years old or more. Oh my God, it's more like 15 years old. It's old. But all of this, one can demonstrate, again, using the math that I've hopefully taught you how to do, one can demonstrate that this chunk of matter can, you know, can interact to form other chunks of matter that have what we would call in particle physics the sort of the preservation of lepton number and the preservation of baryon number, but the no preservation of mesonic number. Yes, that is a curiosity in this theory as well. That is to say that when you actually look at this matter, when you look at these structures and you allow them to decay or you allow them to interact, and you ask, what does it make? What does it decay into? Yada, yada, yada. And then you ask the further question, is there something that seems to be conserved here? Do we find that baryonic matter, initial baryonic matter, is producing final baryonic matter? Do we find that initial leptonic matter is producing the same leptonic chunks or the same number of leptonic matter in the final, in the decay? Do we find that mesonic matter is producing mesonic matter and that there's a conserved quantity going on? And we find that the answer fits exactly what we see in the scheme of particle physics. And we also see that there's another conserved quantity going on, and we'll get to that later. So we're able to grasp particle physics very easily, very directly, and get out of it something so quintessentially important in particle physics, which is what chunk of matter are you getting out? We're going to get to the point where we can actually describe the momenta and the charge and all of those quantities and the energy density and all of those things that the matter can produce. But what's really important to define now that is really so quintessential about this theory as well is that we can define the particle. Okay? That's what you do in the laboratory. What you're really looking to do is to say, that was an electron. Otherwise, if you can't define the particle, then there's really no particle physics. I mean, if all you're defining are energy and momenta of something, that's not really telling you a whole great deal of stuff. What's really giving you the identity, or what's really giving you something is, why is it that nature has these identities to it? Why does it produce 20 electrons and 12 positrons and a couple of protons and a couple of neutrons. Why does it produce that in these particle reactions? And so that's what's going on here. This is a non-perturbative theory of particle interaction, okay? And in this version of the theory that I'm showing you, in this mode of the theory, what we are able to do is to identify the particle and then to watch and see if that particle actually shows up in other particle reactions, and then to go to the laboratory and to see whether that really does happen. And the answer, astonishingly, is yes, it does. So I'm going to end this one, and I want to show you one of my favorites in the next series, sorry, in the next lecture, but one of my favorite things of all time. But, we'll get to that.